All right. This one is number 9.5 in your textbook. And it says, a child is pushing a merry-go-round. The angle through which the merry-go-round has turned varies with time according to theta equals gamma t minus beta t cubed, where gamma equals 0.400 radians per second, and beta equals 0.0120 radians per second cubed. Calculate the angular velocity of the merry-go-round as a function of time. What is the initial value of the angular velocity? Calculate the instantaneous value of the angular velocity omega z at t equals 5 seconds, and the average angular velocity omega average for the interval t equals 0 to t equals 5 seconds. Show that omega average is not equal to the average of the instantaneous angular velocities at t equals 0 and t equals 5 seconds. Explain.
Is that an R or B? That's gamma of.
Oh, that's gamma, and that's beta.
Oh, okay. That is
All right. So omega equals d theta dt. So let's go ahead and write this as theta equals 0.400 radians per second t minus 0.0120 radians second cubed t cubed. Okay. So this is going to equal to 0.400 radians per second minus 3 times 0.0120 radians per second cubed t squared. All right, now what am I supposed to do? Okay, that's calculate the angular velocity of the merry-go-round as a function of time. Boom, that's there. What is the initial value of the angular velocity? Okay, so omega at t equals 0 equals this. 0.400 radians per second, right? Because if I pop 0 in there, that term goes to 0. Okay, the average. All right. Omega average for the time interval 0 to 5. Okay, so omega average is delta, okay, omega average is delta theta delta t. So, delta theta at t equals 5 seconds, or theta, I'm sorry, not delta theta, t equals 5 seconds, is going to be, let's see, equals 0.400 radians per second times 5 seconds minus 0.0120 radians second cubed times 5 seconds quantity cubed. And boy, I wish I would have written that one down. Oh, I got it. It's 3.50 radians. Okay, so this is 3.50 radians. And omega, or theta at t equals 0 seconds is going to be 0, right? Because that term goes to 0 and that term goes to 0. All right, so omega average equals 3.50 radians minus 0 over 5 seconds minus 0. I don't know what that is. Hope I wrote that down. 0.700 radians per second. Okay. All right, the average of the instantaneous velocities, let's see what we get here. So I put 5 here, 5 there, and hopefully I've solved that. Oh, good.
Wait,
The average of the instantaneous, did I do something wrong?
oh, I got a different answer
For here, what did you get?
I got 0.5 radians for the angle.
No, that's correct.
It's correct? Okay,
Yeah.
never mind.
Is it right?
Yeah.
Okay. Okay, now for the average of the instantaneous velocities. Okay, so, I didn't want 5 there, I'm sorry, my bad. Let's see, we have omega at t equals 5 is going to be equal to 0.400 radians per second minus 3 times 0.0120 radians per second cubed times 5 seconds squared. I don't know what that is, but I'll find out. Okay, 3 times 0.0120 times 5 squared. 0.9, so this is, okay,
Yeah, I got 0.5.
times negative 1.
Yeah, shouldn't it be 2 minus 1.5
Where are we?
at t
We're still on
equals
the
5?
average then, because I said it was 0.5.
Yeah, that's 0.5.
For here, you got 0.5?
Yeah. Not for the
T equals 5.
3.5 divided by 5 is
Wait.
No, it's not 3.5.
Okay, so where did we go wrong? Did you say this is incorrect? Right
Yes.
there?
0.5.
What is that?
0.5.
Okay, 0.5. So now what do we have? So now what is this? 0.1?
0.1, I think.
0.1. Okay, thank you.
Shouldn't you change the top too?
Oh, the data t equals 5.
Oh, right, okay. There. Thank you very kindly, everybody. All right, back to here? Okay. All right, so what did you guys get for this? Let's see. 0.4, minus 3 times 25 times 0.012. I get negative 0.05? Negative 0.5? Okay. Radians per second. And then that's omega at t equals 0 is going to equal to just 0.4 radians per second, right? Okay? Because this term goes away. So, omega instantaneous average is going to equal to 1/2 times final minus both of them, right? 0.400 radians per second plus a negative 0.5 radians per second. Okay. Plus 0.4 divided by 2. I get a negative 0.05 radians per second. Is that what y'all got? For the average of the two?
Yeah.
What does it say? W or
Instantaneous omega, not W, omega instantaneous average. Okay, good. All right, to recap. You think the recap is helpful, right? We were given a equation expression for theta. It's got a cube right here. So we know we don't have a constant angular acceleration, so we have to use calculus. The problem wanted us to get an expression for omega, and we differentiated to do that, to achieve that, and we got this. Once we were done with that, it wanted to know the average.
At t equals 5 first.
Yeah, from 0 to 5, right? Okay. So we got the average by solving for delta theta delta t, right? So we got our two expressions for theta at 5 and theta at 0, and we took our average that way. Then the problem wanted the average of the instantaneous velocities at those two times. So we actually solved for the angular velocity at t equals 5 and the angular velocity at t equals 0, and then added them together and divided by 2 to get the average that way. All right, good. Can we, Ruben?